Have you ever just, stopped and looked up at the ceiling in your own home, maybe? Or glanced at one of those massive skyscrapers downtown and really wondered, what's holding all that up?
Right. What's the magic behind it? Even a simple garden shed, keeping the rain out.
Exactly. Let alone a huge office complex where thousands of people are working safely every single day.
Yeah.
It's something we're around constantly, but, well, we barely give it a second thought.
Mm-hmm.
But underneath that, the facade, there's this incredible, really intricate world. Engineering, planning, countless different parts all working together.
In perfect harmony, hopefully.
Hopefully. Okay, let's unpack this. Today, we're doing a deep dive into something, well, really fundamental, something that shapes our cities, our daily lives, the anatomy of a building. Our mission, really, is to peel back those layers, take a comprehensive look at the core bits of these structures, from the ground up.
And even below ground.
Oh, yeah, absolutely. Even what's deep beneath the ground. So whether you're just curious, maybe you're thinking about architecture, or, you just want to appreciate the complexity all around you.
Yeah.
This deep dive, we think, will give you a kind of shortcut, a way to get informed about this hidden world that supports everything we see. We'll look at the foundations, the systems inside that make it work.
Like the building's organs.
Exactly.
Yeah.
And the incredible loads they have to handle. Constantly, we'll connect the dots, show how all these bits and pieces come together to make something that actually functions.
And what's truly fascinating here, I think, is how even structures that seem really simple, like a basic single-story house, they're still the result of some pretty sophisticated design principles. It's this delicate balance, almost like a ballet, managing these huge forces.
A ballet of forces. I like that.
And our sources, they give us this really detailed blueprint for understanding it all. So we're going to trace that blueprint for you, show exactly why each part isn't just like a piece of Lego, but absolutely crucial for the building's integrity, its safety, its usability over the long haul. We'll really get into that interconnectedness, how these things manage to stand strong for decades, maybe centuries, against, well, everything. Nature, wear and tear.
Okay. So let's start right at the beginning then. The absolute basics. What is a building, really, fundamentally?
Well, the core definition we're working with describes it as a relatively permanent enclosed structure constructed over a plot of land for habitable use.
Relatively permanent.
Yeah.
That's interesting phrasing, isn't it? It immediately makes you think, okay, this isn't like a tent you put up for the weekend.
Exactly. Or a temporary stage for a festival. Buildings are meant to last. They're designed for endurance, to stick around for a good long while.
And the habitable use part, that seems key too.
Oh, absolutely key. It means it's designed specifically for people to occupy it or to do things inside it. It's not just houses, right?
Right, so offices.
Offices are habitable. Yeah. Schools, definitely habitable. Hospitals where people are healing. Even a warehouse. It might mainly store goods, but it's still designed for workers to move around inside, manage things, operate machinery.
Okay, so the purpose is providing that controlled shelter, a functional space for people or their activities. And the permanence gives it stability, safety.
Exactly, for whatever it's intended for. That human interaction, that specific activity, that's really what elevates a structure to being a building.
Got it. So when we look closer, you're saying every building, no matter the size or what it's used for, kind of breaks down into three main parts, like body parts.
That's a good way to think about it. 3 core divisions. The first one, and you could argue it's the most crucial, is the foundation.
The foundation. Okay.
Often called the building's feet. It's the structural part that has the huge job of transferring the entire weight of the building onto the ground underneath it.
The entire weight.
Every last bit. It's that critical connection point, the interface between the structure and the earth itself. Without a good foundation, properly designed, carefully built, the whole thing is just unstable.
Right. You can't just build on bare dirt.
Imagine trying. Standing a multi-story building right on loose soil, it would just settle unevenly. You'd get cracks everywhere.
Yeah, disaster.
Potentially catastrophic failure. So the foundation's main job is to take all that concentrated weight coming down and spread it out. Distribute it over a wide enough area of soil.
Spreading the load.
Exactly. So the pressure, the pounds per square foot, doesn't exceed what the soil can naturally handle its bearing capacity.
The soil's strength limit, basically.
Precisely. It prevents the ground from squishing down too much or failing. It's the unsung hero, really, always down there, out of sight, fighting gravity.
That makes total sense, like the roots of a giant tree. Anchoring it.
Yeah.
Okay, so after the foundation, what's the second major part? You said it's sometimes overlooked.
That's the substructure. It's defined as the habitable part of the building below ground.
Habitable below ground. Okay, so basements?
Basements are the classic example. Or crawl spaces. Even though they're out of sight, these areas can be incredibly useful. A basement is usually a full story, sometimes more, below ground, often finished, used for living space, utilities, storage.
Right. And crawl spaces.
Crawl spaces are typically smaller, unfinished, usually less than a full story high, just under the first floor.
Thanks. Crawl.
You got it. But both are part of the substructure. They act as this important buffer between the ground and the main living areas.
A buffer. How so?
Well, they help protect against ground moisture, temperature swings, and they often house the guts of the building, plumbing, wiring, HVAC ducts.
Ah, okay. So habitable here means enclosed, controlled space, even if you're not, like, living down there full time.
Exactly. They play a really crucial role in the building's overall health and how it functions day to day.
Okay. Foundation, substructure, and then the third part, the bit we all see.
That's the superstructure, simple definition. The part of the building above ground.
Basically everything else.
Pretty much everything you see and interact with, from the ground floor right up to the very top of the roof.
Walls, floors, roof.
All the walls enclosing spaces, all the upper floors creating different levels, the whole roof system, windows, doors. Essentially all the visible stuff that gives a building its shape, its function, its look.
That's where the architecture really happens, visually speaking.
Absolutely. It's where most of the human activity goes on. So understanding these three big divisions, foundation, substructure, superstructure, gives you a really solid framework for looking at any building, big or small.
They're distinct parts, but totally connected.
Deeply connected. Each serves a unique, vital purpose in making sure the building stands up and does what it's supposed to do. So with that big picture, we can now sort of zoom in a bit.
Yeah, let's peel back another layer, get into the specific components, the systems, the real anatomy.
All right, let's do it.
So keeping those three big parts in mind, the base, the below ground bit, and everything above, let's zoom right in. Look at the specific organs, maybe the skeleton, that makes up each part. And it all starts, naturally, with the building site.
You can't build thin air.
Exactly. You need land and the site itself, what the soil is like, if it slopes, what's around it, how much sun or wind it gets. That's fundamental to the whole design.
Right? Absolutely fundamental. You don't just drop a building anywhere. You design for that specific piece of earth. The site conditions dictate so much.
Including, as you said, what kind of foundation you need.
Precisely.
Yep.
Which is why the foundation gets listed again here as a specific component. It just hammers home how critical that connection to the ground is. Can't overstate it.
Okay. So from that stable base we build up, what's next on the component list? Floor systems.
The horizontal surfaces we walk on, they define the levels in a multi-story building. And they're not just flat surfaces. They're engineered to carry weight. Significant weight.
And holding up the floors or enclosing the space, we have wall systems.
The vertical bits, they enclose, they divide rooms, but they're also often structural, carrying loads downwards and providing privacy, of course.
Right.
Yeah.
And within those walls, you need openings, doors and windows.
More than just looks. They're essential for getting in and out, for light, for air, ventilation. Imagine a building without them.
A dark, stuffy box. Not very habitable.
Not at all. Then, crucially, there's moisture and thermal protection. This is all about keeping the weather out and keeping the inside comfortable.
So insulation, waterproofing, stuff like that.
Exactly. Insulation, vapor barriers to manage humidity, waterproofing systems, critical stuff for comfort and durability.
And then topping it all off.
Yeah.
Literally, the roof system.
The building's hat, its main job is shelter from rain, snow, sun, wind. The first line of defense against the elements.
Okay. And inside, what makes it livable?
That's finish work. This is what turns the bare structure into somewhere you actually want to be. Paint, flooring, trim, lights, cabinets, all the stuff that makes it look and feel finished.
Got it. And the last one here is special construction. What falls into that?
That covers unique things for specific building types, maybe a super reinforced vault in a bank.
Or like a clean room in a lab.
Exactly.
Wow.
Highly specialized elements or building techniques needed for unusual purposes.
Okay, so those are the components. How do these relate back to the idea of structural parts versus building systems?
That's a really important connection to make. The structural components are basically the building skeleton, the rigid frame that holds everything up and carries the loads.
So the foundation is purely structural.
Absolutely. It's the base. Then floor systems, definitely structural. They hold up people, furniture, everything on them.
Wall systems, too.
Often, yes, very structural. They're not just dividers. They bear weight, resist side forces like wind, provide rigidity. And the roof system, hugely structural. Provides shelter, yes, but also has to handle loads like snow or wind trying to lift it off.
So that's the skeleton. Solid, load-bearing.
Right. But buildings aren't just static skeletons. They're dynamic, almost like living things with these complex, interconnected internal systems.
The building systems. And this is where you said it gets really interesting. Our sources say building systems are the critical systems of a facility. These systems are rarely, if ever, independent entities. Rather, they depend on each other to operate.
That interdependence is so critical to understand. It's not just a random collection of parts. It's a network, like a biological system. If one part fails,
Ripple effect.
big time. Think about the most obvious example. Most building systems rely on the building's base electrical service for power.
Heating, cooling, lights, elevators.
Everything. If the power goes out, most other critical systems are impacted almost immediately. Or a more specific example. Computer systems often need supplemental cooling to operate properly.
Like server rooms needing extra AC.
Exactly. Shows how specialized systems rely on the more general ones, like the HVAC, just to function without, melting down. It's a chain reaction. Pull one string and the whole thing can get tangled.
And managing this web, the sources say, all building systems are typically designed, installed, managed, maintained, and supported by their own team of domain of experts. Sounds complicated. Like coordinating an orchestra.
It is a huge coordination challenge, especially in big projects. You've got electrical engineers, mechanical engineers for HVAC, plumbing experts, IT network people, security system designers.
All specialists.
Highly specialized. And getting all these different teams with their different systems to work together seamlessly, ensuring not just that their system works, but that it integrates properly with all the others for peak performance. It's incredibly complex.
You can see how things could go wrong if they're not coordinated.
Yeah.
HVAC fighting the lighting controls or something.
Total chaos. It impacts comfort, energy use, operations, safety, everything. It really highlights how multidisciplinary modern construction and building management is. It takes a lot of collaboration.
Okay, so let's quickly run through the main types of systems mentioned. First, mechanical systems.
Right. These are mainly about controlling the environment and moving people around. So cooling, heating, and ventilation, HVAC, crucial for comfort, air quality, humidity control.
Yep.
Think about keeping a concert hall cool with thousands of people inside.
Yeah, serious engineering. What else is mechanical?
Conveying systems. So elevators and escalators. Absolutely essential in multi-story buildings for moving people vertically, accessibility. Skyscrapers wouldn't work without them.
True. Okay, next up, plumbing systems. Seems simple pipes, water, but I guess it's more complex in a big building.
Oh, massively complex when you scale it up. Three main parts here. First, water supply, pipes, pumps, fixtures delivering clean water everywhere it's needed, drinking, washing, etc.
Okay.
Second, waste disposal, drains, pipes, sewers, getting rid of wastewater and sewage safely and hygienically. Huge job we take for granted.
Until it stops working.
Exactly. And third, gas system could be LPG for cooking or heating, or specialized gases like oxygen in a hospital.
Right, which would be critical infrastructure there.
Absolutely life support level critical.
And finally, the one that powers pretty much everything else. Electrical systems.
The lifeblood forms the energy backbone.
Yeah.
You've got the basic power outlets, circuits, the main sources feeding everything. Then lighting, not just for seeing, but for ambiance, mood, function. General lighting, accent lights.
And in today's world, telecoms.
Essential. Telephone, internet, cable TV. All the communication and data infrastructure. A modern building just grinds to a halt without robust electrical systems.
So thinking about all these systems, mechanical, plumbing, electrical, they're not just installed and forgotten, right? The source says they're evaluated and controlled both as an independent system and as a part of a larger whole.
Exactly. It implies constant monitoring, adjustment, almost like the building is alive, responding.
How does that integration actually impact things, like energy use?
Hugely. Think energy efficiency. If your heating system isn't talking to your window blinds or your automated lights, you could be heating a room that's already warm from the sun or cooling a space that's empty. Massive waste.
Or maintenance.
Right. A small leak in a pipe plumbing system could drip onto critical electrical gear or data cables. So you need that holistic view, proactive management across systems.
So it's about making the building not just functional, but efficient safe, adaptable.
Precisely. Turning it from just a structure into a responsive, intelligent environment, almost like a living thing.
Okay, that makes sense.
Okay.
Now, let's shift back to the structure itself, the frame, the stuff holding it all
For the
up.
backbone, yeah.
And the key concept here is load, which the source defines simply as a weight or source of pressure borne by someone or something. That's what structural engineers are constantly dealing with, right? Loads.
It's their whole world. Understanding how buildings handle these loads requires looking at the key structural parts. Starting horizontally, where things happen, the floor, defined as the level base surface of a room or hall upon which one stands or walks.
So its job is to provide that flat surface, but also to take the load and pass it down.
Exactly. Collects and distributes the load to whatever is supporting it underneath.
And what is directly underneath. The source mentions joists.
Joists. These are a horizontal structural member used in framing to span an open space, often between beams that subsequently transfer loads to vertical members.
Okay, so picture the ribs under a floor.
That's a great analogy. Smaller, parallel horizontal bits, often wood or steel. When you walk or put furniture down, the floor decking transfers that weight to the joists.
And the joists then pass that load
Onto bigger horizontal members, girders or beams, described as rigid structural members designed to carry and transverse loads across space to supporting elements.
So if joists are ribs, girders and beams are like bigger arteries collecting from the joists.
Exactly right. Girders often support a whole series of joists, collecting their combined load and transferring that to the vertical supports.
And those vertical supports are the columns or posts.
Yep. Defined as rigid, relatively slender structural members designed primarily to support axial compressive loads applied to the ends of the members. Think of them as the vertical bones of the building.
Designed for axial compressive loads. What does that mean exactly?
Axial means the load acts along the length of the column, straight down its center. Compressive means it's a squeezing force. Imagine stacking heavy books on a pole. That downward squeezing is axial compression. Collars are built to be incredibly strong against that crushing force.
So they funnel the weight down from the floors, joists, beams.
Straight down, like a plumbing system, but for weight.
And where does all that collected, channeled weight finally end up?
Back where we started, at the footing and foundation. They take all those accumulated loads from the columns and transfer them to the ground.
And the ultimate endpoint is the site itself. The earth takes the final load.
The ground zero for everything.
So this whole system, this hierarchy of load transfer, what does it really mean for the building's stability and design?
It's the absolute core principle of structural engineering. Every single piece, from a tiny joist to a massive column, is designed to safely pass the load down, down, down to the earth. And this is critical, it's not just the building's own weight they handle.
Ah, right. There are different kinds of loads.
Exactly. Buildings have to withstand various types of loads, and our sources break them down into 4 main categories. Each one presents its own challenge.
Okay, let's tackle them. First one sounds simplest. 1, dead load, defined as fixed static loads made up of the building's own structure, skin, equipment, and other fixed elements.
These are the constant, predictable ones.
Yeah.
Think the weight of the concrete, the steel frame, the drywall, the roof tiles, the windows. Even big permanent things like a heavy HVAC unit on the roof.
Stuff that doesn't move.
Exactly. It's inherent to the building itself. It's there from day one and doesn't change. Engineers calculate these very precisely because they form the baseline, the constant burden the structure always carries.
Okay, dead loads are fixed. What's the opposite?
Live load, defined as moving or transient loads such as occupants, furnishing, rain, snow, and ice.
Ah, so anything that can move or change. People walking around.
People, furniture being rearranged, heavy snow piling up on the roof, rainwater ponding. These loads are dynamic, variable.
How do you design for something that changes?
That's where building codes come in. They specify minimum live loads for different building uses. A library, for instance, needs to support way more weight, all those books, than a typical house.
Or a dance studio versus an office?
Exactly. Roofs in snowy areas have to be designed for heavy snow loads. So while the exact load isn't known moment to moment, engineers design for the maximum anticipated live load for that building type and location.
Got it. Okay, dead loads, live loads, what's next?
Environmental forces, specifically 3, wind load, described as pressure from wind that affects lateral loads as well as possible uplift forces or downward pressure.
Lateral loads, meaning sideways pressure, pushing the building over.
That's a big part of it, yes. Wind pushes horizontally against the sides, but it's more complex than that. Wind swirling around a building can also create uplift, trying to literally suck the roof off.
Wow.
Or even create intense downward pressure on certain parts of the roof, depending on the shape and wind direction. Wind is incredibly dynamic gusts, eddies. It's a complex force to model.
Especially for tall buildings.
Absolutely. Tall buildings are designed to sway slightly, almost imperceptibly, to absorb and dissipate that wind energy without getting damaged over time. Watching buildings withstand hurricanes, that's them fighting immense wind loads.
Incredible. Okay, fourth category. 4. Other load dynamic includes impact loads, shock waves, vibrations, and seismic load. Sounds like the dramatic stuff.
These are definitely the wild cards. Unpredictable, often violent. Impact load like a car hitting the building or something heavy being dropped.
Okay.
Shock waves maybe from a nearby explosion. Vibrations could be from heavy machinery running inside or even constant traffic nearby. And then seismic load earthquakes.
Earthquakes must be the toughest challenge.
Arguably, yes. The forces are intense, multi-directional, side to side, up and down, even twisting. Buildings in earthquake zones need very special designs.
Like what?
Often things that allow flexibility and energy absorption. Base isolation systems that let the building sort of float on bearings during a quake, or damping systems that act like giant shock absorbers. It's about resilience, designing to bend without breaking, essentially.
So engineers have to account for all 4 types.
Yeah.
Dead, live, wind, and these dynamic loads.
Every single one.
Yeah.
They all factor into how a building is designed and how it performs safely over its whole life.
Okay, we've traced those loads all the way down through the joists, beams, columns, landing right back at the bottom. So let's circle back and really focus on the foundation.
The anchor.
Exactly. The definition again. The lowest division, partly or wholly below the surface, designed to support and anchor the superstructure and transmit its loads directly to the earth. It's that crucial link.
And within the foundation, that key component is the footing. Remember the definition, part of the foundation bearing directly upon the supporting soil.
Where the building actually touches the ground.
Precisely. And the footing's design depends entirely on the soil it's sitting on. That's why before they build, they do soil tests, geotechnical analysis.
Drilling down, taking samples.
Yep. To figure out what the soil is made of and, crucially, its bearing capacity. How much weight can it safely hold without squishing or failing? That info is absolutely vital for sizing the footing correctly.
To make sure it can spread the load properly for that specific soil.
Exactly.
So how does it actually work? How does the foundation do its job? The sources break it down step by step.
Right, let's walk through that physics. It's a hidden dance of forces. Step 1. The loads of the building structure are transmitted down vertically through the columns.
Okay, weight travels down the columns.
Just like we discussed. From the top floor down through the frame, concentrating into those columns, that's the downward journey.
Then step 2. The column, connected to a footing which spreads the load over a wide enough area of soil, provided that the bearing capacity of the soil is not exceeded.
This is the magic trick. That concentrated load coming down the column is too intense for the soil by itself. The footing acts like a snowshoe or an upside-down pyramid base.
Spreading the pressure out.
Dramatically. It takes that point load and distributes it over a much larger soil area. This lowers the pressure per square foot below the soil's bearing capacity, its strength limit. If you exceed that limit, the building sinks unevenly. Bad news.
Got it. Prevents it from punching into the ground.
Exactly. Now, step 3. The soil pushes up against the footing. This causes tension at the bottom side of the footing and compression on the top side. Reinforced concrete footings have reinforcing bars at the bottom because, and the source kind of trails off there, but the because is correct.
The soil pushes back up. Newton's third law.
Precisely. Equal and opposite reaction. Building pushes down, soil pushes up. This upward push from the soil creates stress inside the footing.
Okay.
On the top of the footing, right under the column, the concrete gets squeezed. That's compression. Concrete is great at handling compression, really strong. But on the bottom of the footing where the soil is pushing up, the concrete is being pulled apart, stretched, that's tension. And concrete is terrible in tension. It cracks easily.
So that's why they put steel bars in it.
Yeah.
They're B-bar.
Bingo. That's exactly why. Steel reinforcing bars, rebar, are incredibly strong in tension. So when the soil pushes up and tries to stretch the bottom of the footing, the rebar takes that pulling force, preventing the concrete from cracking.
Wow. So it's a team effort. Concrete for compression, steel for tension.
A brilliant combination of materials, leveraging the strengths of both to create something incredibly strong and durable. It's that unseen anchor, constantly in this tug of war, gravity pulling down, earth pushing up, happening right now beneath our feet.
Mind blown. Okay, so that explains the rebar cages you see before they pour concrete foundations. It's structural necessity. Now, moving from the mechanics, let's talk about the actual spaces below ground.
Yeah.
The substructures. 3 main types, you said.
Yep, 3 main approaches, balancing cost, function, site conditions. First is 1, slab on fill. Described as a slab which rests on ground and not suspended.
So just a concrete slab poured right on the prepared ground.
Pretty much. Common in warmer places where you don't worry about frost heave or where the soil is really stable. They prep the ground, maybe put down gravel fill, then pour the concrete floor slab directly on that. Simple, cost-effective, no space underneath.
Okay, what's the next type? 2, crawl space. Sounds cramped.
It usually is. Defined as, in a building without a basement, an unfinished accessible space below the first floor, which is usually less than a full story height.
So there is a space underneath, unlike the slab.
Yes, an enclosed gap between the ground and the floor above. It's tight, hence crawl, but super useful.
Useful how?
Great for getting access to plumbing, wiring, HVAC ducts for repairs or upgrades. Plus, it allows for ventilation under the floor, which helps manage moisture, prevent mold, maybe vent radon gas.
So it's a practical middle ground if you don't need a full basement.
Exactly. A common choice when some underfloor access and separation from the ground is needed, but a deep excavation isn't justified.
Which brings us to the third type. 3, basement. Defined as the lower story of a building, either partly or entirely below grade.
The full depth option requires significant excavation to create a full height story below ground.
Often finished space, right? Like living areas.
Very often. Basements can add huge amounts of usable square footage, rec rooms, bedrooms, offices, workshops, lots of storage. They effectively double the house's usable space without making the building physically wider or longer on the lot.
But they must be more complex to build.
Oh, definitely. Big excavation challenges, potential groundwater issues means serious waterproofing is needed. Managing dampness requires good ventilation or dehumidifiers.
Worth it for the extra space, though, often.
For many people, absolutely. And in cold climates where foundations have to go deep anyway to get below the frost line, building a full basement often makes sense because you're already digging down that far.
So slab, crawl space, basement. Different ways to connect to the earth depending on needs and location.
Each a tailored solution.
Okay, we've got the theory, the components, the systems, the foundation. Now, how does construction actually start on site? The very first physical step.
That would be staking out the building.
Staking out. Sounds like claiming territory.
In a way, it is. It's about precisely marking out where the building will sit on the land. The definition is the driving of stakes for batter boards to locate the corners and foundations of a building for excavation.
And precision here is key.
Absolutely critical, non-negotiable. Any mistake, now a few inches off, an angle not quite right, will cause headaches throughout the entire build. Walls won't be straight, rooms won't be square. Fixing it later is expensive and time-consuming. This step is the foundation for accuracy.
Before you even hammer in the first stake, though, there's homework to do.
Crucial homework. The source advises. Before staking out, it is advisable to go through the process of relocating the point of boundaries and property line of the site.
Making sure you know exactly where your property lines are.
Exactly. You need to avoid building on your neighbor's land, obviously. And you need to make sure the building location meets all the local zoning rules about setbacks, how far it has to be from the street, from the sidelines, the back line.
So you might need a surveyor for that.
Often, yes. A professional land surveyor uses special gear to find the official property markers, the monuments, and confirm the legal boundaries. Get that wrong, and you're in a world of trouble.
Okay. Property lines confirmed. Now we can start staking. Let's walk through the steps.
All right, grab your tape measure and string line. Step 1, establish the front building line. You measure the required setback from the front corner monuments, drive 2 stakes, and stretch a string between them to represent the front building line.
So that string shows exactly where the front face of the building will be, parallel to the property line or street.
Perfectly straight, your first reference line. Now, step 2. Pinpoint the first corners, A and B. You measure the required side setback from one of the side lot lines along the front building line. Drive stake A, which will represent the first corner. From stake A, measure the width of the building and mark with stake B.
So you find one corner based on the side setbacks and measure across the planned width to find the other front corner. Now you have the exact start and end points of the front wall.
Correct. The front face is defined. Now, step 3. Lay out the rear corners, C and D. From stakes A and B, you estimate right angles and measure the length of the building. Drive 2 temporary stakes C and D. CD should be equal to AB.
Estimate right angles. How do you make sure they are right angles?
Good question. You can use the 3-4-5 triangle method or large framing squares. But the crucial check comes next. The key here is extending the sidelines back the correct length and ensuring the back width, CD, matches the front width, AB.
And that crucial check for squareness.
Step 4. Check the diagonals. You draw lines along the diagonals AD and BC and ensure that these are equal. Basic geometry. If it's a perfect rectangle or square, the diagonals must be equal.
If they're not equal?
It means your corners aren't truly 90 degrees. Your building outline is skewed, a parallelogram. You have to adjust stakes A, B, C, or D slightly until those diagonals measure exactly the same. This confirms perfect squareness before you dig.
Clever. Simple but effective. Okay, it's square. What's the last step? Step 5, transfer to batter boards.
This preserves that accuracy. Batter boards are temporary wooden frames built a little outside the corners of where you'll excavate, usually like T-shapes sticking out of the ground.
Outside the digging area, why?
So they don't get knocked over during excavation, you carefully transfer the exact building lines from your strings onto the top edges of these batter boards, often with a saw cut or a nail.
So you can take the original strings down while they dig.
Exactly. The strings would get in the way, but the marks on the batter board stay put high and dry. Later, builders can re-stretch strings between the marks on opposite batter boards to perfectly re-establish the building lines whenever they need them for setting foundation forms, for example. It keeps the reference points safe and accurate throughout construction.
That's ingenious. A simple wooden frame holds the key to the whole building's alignment.
It really is elegant site engineering.
And the tools are basic too. Stakes. Wooden sticks, sharpened at one end, driven into the ground.
Just simple posts to hold the strings or support the batter boards?
In strings. Plastic cords or galvanized wires strung across batter boards to indicate the outline.
Basic. But when used with care and precision, they lay the literal groundwork for everything that follows. It's this quiet, meticulous setup that happens before the heavy machinery even arrives.
Wow. Okay, we have covered a lot today. From the big picture definition down to the tiny details of loads, the physics of foundations, and even hammering stakes into the ground.
It's quite the journey from concept to concrete.
What stands out is how interconnected everything is. The visible superstructure relies totally on the hidden foundation, and the whole thing needs those complex systems to actually function.
Nothing works in isolation.
So what does this all mean for you, the listener? When you walk into a building next time, what's the takeaway?
I think fundamentally understanding these hidden elements just gives you a much deeper appreciation, right? It lets you think more critically about the spaces we use every single day.
Stops being just walls and a roof.
Exactly. It becomes this marvel of engineering, coordination, resilience, and it raises an important question, I think.
Which is?
How might knowing about this hidden skeleton, these organs of a building, how might that change how we interact with our built environment, how we design it, how we adapt it for the future? Thinking about challenges like climate change, population growth.
How can we make buildings smarter, more resilient, more adaptable by understanding their anatomy better?
Precisely. It's not just about putting up structures anymore. It's about creating these intelligent, responsive habitats that can genuinely stand the test of time, weather, and whatever else we throw at them. The world under the floorboards and behind the drywall, it's way more complex and way more vital than most of us realize.
A lot to think about next time you walk through a door.